Okay, so one example it talks about here, this is a cubic. So you might recall we talked a little bit about graphing quadratics in the past. And all you really need to know about if you want to like graph a quadratic, all you have to do there is if you know where the vertex is, right? Then you can plot the vertex. You know if it's going to be upward facing or downward facing based on the fact if the leading coefficient is positive or negative. And that leading coefficient is just the coefficient on the x squared term, right? And then you can kind of then base it off of the parent function and then stretch it up or down. So if you have like the leading coefficient is like positive 2, then you would just start at that vertex and then you would graph the parent function of the quadratic, which is just the normal shape moving over 1, up 1, over 2, up 4, right? But you would want to multiply all the y values by 2 to account for that leading coefficient being something other than 1, right? To give it that kind of stretch. I've already talked about that a lot though. So I mean, if you guys want me to talk about that more, I can, but that's not what this chapter is about. That's just a little bit of a preface. Here's a cubic though. So this is obviously slightly more complicated than a quadratic because we have this additional term here. And what we find with these kinds of polynomials is that whenever I'm graphing them and I move away from x equals 0, it's this highest order term that's really going to dominate the main behavior of the graph. This is what matters most because you'll notice if x is like something other than like a very small number, if x is non-negligible, if it's like greater than like 2 or something, I don't know exactly, but this is the term that's going to have the most influence because like if I give you like if I pick like 3 squared is 27, or 3 cubed is 27, 3 squared is 9, 3 is just 3, and then this is unaffected. So as x gets large, this term is going to get larger a lot faster than the other terms. So we can interpret or like infer most of the behavior of a graph like this just by looking at this. So what I know immediately when looking at this is I know and you guys might not recognize this immediately, but that's okay. Just follow what I'm talking about. I know that as x goes to infinity, this graph is going to go way up to infinity, right? And as x goes down, this is the x-axis, this is the y-axis. As x moves towards negative infinity, the graph is going to move towards negative infinity because that's what this term is doing. That's what the cube term is doing, right? As x goes to negative infinity, x cubed goes to negative infinity. That's what this is doing, and this term is going to be dominating for larger values of x. So I already kind of can tell like what the shape of this graph is going to look like. If this was a negative here, then I would flip it, right? If this was a negative on the leading coefficient, then as x went to positive infinity, y would be going to negative infinity, right? It would be the reverse. But no, this is a positive number here in this example, so that's that. So then if I want to graph the remainder of this, remaining questions that lie are what does it kind of look like near x equals 0? Because if x is small, then this term isn't going to be the only term having influence. All of these are going to kind of play an effect into what exactly the graph shape is going to look like, right? So that's a question that we need to answer. And one useful question to ask while answering that is what are the zeros? Where are the points where this graph intersects with the x-axis? Because if I know those, that can help me a lot with filling in the shape of the graph. Because then if I know if it has like 3 zeros, then I would probably go up, down, back up. If it only has 1 0, then maybe it just goes like that. I don't know. So that's a question that I'm going to try and answer here. So I'm going to set 2x cubed plus x squared minus 8x minus 4 equals 0, right? And I'm hoping that you guys are a little bit familiar with this. I'm going to use a concept called factoring by grouping, right? And I'll talk about that a little bit, but I'm going to assume that he's gone over it. I would assume, but I don't know. Regardless of if he has or not. Essentially what that is I'm looking at these two terms and I'm looking at these two terms, right? So I'm splitting it up a little bit. And I'm going to factor something out of both of them. So here I notice common factors of this term is just going to be x squared. I can replace this. I can make it x squared times 2x plus 1. And then common factor of this term is minus 4. So I can write this as minus 4 times 2x plus 1. And then this is equal to 0. So you'll notice I factor a common term of this term and a common term of this term, right? So hopefully that's not outrageous to anybody. I'm just, factoring something out there. And then you should see that these are equivalent if I distributed this. Anyway, I now have something that looks like this, and I can do a little bit more with this to clean it up. You'll notice this kind of looks like what if I had this term is now a common term of both of these, this 2x plus 1 term. So this kind of looks like if I had this 2x plus 1, and then I had the x squared minus 4. Because you'll notice these are actually equivalent, because if I took this 2x plus 1 and I if I distributed it to both of these, I would get this back. So if I took this 2x plus 1 and distribute it to both the x squared term and the minus 4 term, I get this back. And then if I distributed the x squared, I distributed the minus 4, I would get back to here. So all I'm doing is I'm doing sort of a sequence of factoring. And then this kind of method of factoring these two things independently and then getting something that looks like this, this is just a process called factoring by grouping. So, I mean, if you look at the math, the reverse direction should be pretty clear to you that this is equivalent with this, because I can distribute and I distribute again, right? The factoring itself, that might be less obvious while I was doing that, or like how would you come up with knowing to do that? But again, you should see that it's okay because the other direction is fine. Anyway, I have this 2x plus 1, and then I can factor this. This is a difference of squares. So this is x plus 2 times x minus 2. Anytime I have something in the form a squared minus b squared, this is always equal to a plus b times a minus b. And then you can show this by doing the foiling of this. So I get the a squared for the first terms minus ab for the outside terms plus ab for the inside terms, and then minus b squared for the last term. And then the minus ab cancels with this, so I get the a squared minus b squared back. Anyway, all I'm saying here is that this is in the form a squared minus b squared, because this is x squared minus 2 squared. So I can factor it like this, and I get this. So this is all equal to 0, okay? So then I have this, and then now that I have this is all factored up, I can tell where the zeros are kind of faster. I can say that x equals minus 1/2. If x equals minus 1/2, then this term's going to go to 0, and if this term's 0, then the whole thing goes to 0, so the function equals 0 at this value. It's also going to equal 0 at -2 and +2. So these are my 3 zeros, and then I can kind of plot them. I didn't really sketch out this x-axis, but you guys can follow what I'm doing here. I'm going to say that -1/2 is here, -2 looks like, oh, maybe that's about there, and then +2, that's over here. And then when I'm kind of moving between these zeros, I kind of weave my graph so it hits all of the zeros. I do something like this. I know it's going to go through this because it's going down here, and then it's going to loop around, and because I want to hit all of the zeros, and I still want to have the valid end behavior of the graph, because that's the main idea I was talking about earlier, this idea of end behavior being dominated by this leading term. So then, yeah, then I know my graph's going to look something like this. This is the shape of the graph, graphing polynomials. Here it is. And then, you could be like, hey, well, this is kind of just like a cute little sketch, but I only really plotted 3 points. Is there a way I could make it more exact? And yeah, I mean, I could find more points. Maybe I want to know where, like, what does the graph equal if I plug in x equals 1? Okay, well, that's a question that you can answer. If I just plug in 1 for x, I get a value out for y, because this function tells me how x values relate to y values. So I could plot as many points as I like. I could get more. And that's great. I'm sure your graph will look really accurate and cute once you're all done with that, and that's perfectly fine. But the main idea with algebra is, like, I mean, that's not really that interesting though. Just picking random points, plugging them in, making the graph look kind of cuter. It doesn't really matter at that point. The main thing that matters is, are you getting the general shape right? Right? Do you know where the zeros are? Can you find the zeros? And do you know what the end behavior is? Because if you know both of those things, the zeros and the end behavior, then you should be able to get a general picture of what the graph looks like. And then that's like most of the interesting math that you'll be doing. That's what's really important here. So focus on getting this kind of a shape graph. If you see this kind of a polynomial, can you derive something like this if you know the end behavior and you can find the zeros? So that's an important skill. One note I want to say is that I was able to factor this by grouping, there's no guarantee that you'll be able to do that, because you can tell, like, I factored this out here, I factored this out here, and these happen to be the same. It's honestly a little bit convenient that these were the same. That's just the case with these textbook problems. Sometimes they'll be the same. And often with your problems, you'll see they will be the same because problems you're given will be designed such that they work out in a convenient way so that you don't get too tripped up on the algebra. Because this is like really the important thing, is if you can do this kind of thing, then that shows you generally know what you're doing. Even though not all cubic functions can be factored by grouping like that. And if they can't be factored by grouping, there are other ways of going about it. But that's the specific methods. I mean, like they're good to know, but they're not really the central of what's important here. The important thing here is, like, do you understand how the end behavior works, and can you work out what the zeros are in the situation where it factors somewhat easily? Yeah, that's really what's most important here. Okay, does anybody have questions about that? Thoughts, doubts, comments? Okay. So, I mean, I could do more of these. We could go through some other examples if you want with graphing polynomials. But the main thing that's important is, in all of these examples, the end behavior, that sort of technique is going to be the same. If it's an odd polynomial, then you'll notice one pattern you'll see with odd polynomials is they always, to positive infinity, if they go off to, as x goes to positive infinity, if y goes to positive infinity, then it's going to go to negative infinity the other way. Let me try and say that better. For an odd function, it's going to have this pattern where the end behavior in both directions aren't the same. But for an even function, the end behavior in both directions will be the same. And that's something you see with, like, parabolas. The end behavior as we go off to positive infinity and negative infinity, it's always going to be the same. For downward facing parabola, it goes negative in both directions, right? No matter which x direction I travel along, it's going to go down into the negatives, or it will go up into the positives. But the point is, for a parabola like this, they're always going to be the same. And this isn't just the case with typical second order polynomial parabolas. This is the case with, you know, if your highest power is x to the 4, then it's also going to look kind of similar. It might look a little bit different near x equals 0 because the lower order terms are going to have more influence. However, it will look the same as you're going off to infinity in either direction. Yes, good, good. All right, I'm going to mention some other things that are mentioned in this section. It looks like one thing that they throw out here is the intermediate value theorem. And I suppose it's important to know what that is going through life. Maybe it will come up. I don't know. Everyday real world problems. The point of the intermediate value theorem is that if I have some kind of, like, a continuous function, and then I haven't, continuous isn't really a well-defined term right now, but you can imagine all that it means is, like, the graph is connected everywhere. It's kind of smooth like this. Like this function, if I drew another function over here, this function, maybe this is like a piecewise function, this one's not continuous. So for a function like this has kind of a break in the graph, oh, it's kind of getting a little bit fuzzy. Will you refocus, please? Okay. Anyway, if there's a break in the graph, that's what we call, like, a discontinuity, then this doesn't apply. So but if you don't have any breaks in the graph, if you have just a normal function like this, some clean function, then one thing that we can say that is, if I have some interval a to b, this is x equals a, this is x equals b, because this is the x-axis, this is the y-axis. Of course, the function is going to, if we're assuming it exists everywhere in this interval and there's no breaks in the graph in this interval, here is b, so then there's going to be some f of a here on the y-axis and some, f of b here farther along on the y-axis. So if this is a continuous function, if there's no breaks in the graph, then what the intermediate value theorem says that for any given number, I guess I will pick D, such that D is between f of B and f of A. For any given number in this range, so we see that this is f of B on this graph, this is f of A. So if I pick a number in this interval, then there exists a number in this interval. There exists a number in this interval, I'm going to call it C. There exists such that f of C is equal to D. Okay, so let's say, like, I don't know, maybe the number 5 is in this interval here. And then I go over, if 5 is in this interval between f of B and f of A, then there has to exist some number between A and B. Maybe this is pretty close to B, it looks like here. But there has to exist some number C such that f of C is equal to 5 in this specific case. Okay, that's a specific kind of like a theorem, not really an example, but again, I'm just going off of what I heard is that he covered 4.2, so I'm just talking a little bit more about these concepts. Does that kind of make sense what I'm saying here? If I pick a number in this interval, then there has to be a number in this interval such that if I apply this number to the function, the output will be that given number. Okay. All right, is there anything else you guys want me to talk about? I'll keep going, just doing random examples, I guess. But is anybody else aware, like, did he start, or go ahead?
Nothing. I was just gonna say we also got into 4.3 the last two classes.
Okay, yeah, I'll take a look at 4.3 a little bit. How about? Good, thank you. So the main thing to know about, it looks like in 4.3, is polynomial division. And polynomial division can kind of help us understand rational functions a lot better. So the idea with rational functions is, what if I take one polynomial and I divide it by another polynomial? What would the subsequent graph look like? What exactly is going on there? How can I interpret that? So the question is, okay, well, how am I going to interpret the division of two polynomials? And sometimes that's easier to do if you actually physically do long division with those polynomials, right? So let me find an example with that. What's a good one? So I'm going to do one that actually doesn't use the division first in terms of just polynomial, interpreting these polynomials. So if I had something like this, I want to mention one technique to you that I think is pretty useful. This is a polynomial function, but again, it's not super easy to interpret what's going on there. One thing I can always do if I see something this where the numerator and the denominator kind of look similar except for constant terms that they're missing, this is a technique you can use to kind of work around polynomial long division. So I guess instead of doing an example of polynomial long division, I'm telling you how you can get out of it in some instances, but I'll do other polynomial long division examples too. But I want to mention this because it's kind of cool. I like doing stuff like this. This is equal to x squared plus 2x plus 1 minus 1 over x squared plus 2x plus 1. See, I just added and subtracted 1, so I'm not really changing anything. Okay. And then this is equal to x squared plus 2x plus 1 over x squared plus 2x plus 1 minus 1 over x squared plus 2x plus 1, which is equal to 1 minus 1 over x squared plus 2x plus 1. I think this is kind of easier than polynomial long division in some instances, as you can see, because this is the result you would have gotten. You would have gotten a remainder of 1, which is equivalent to putting 1 over this fraction. And then you get 1 minus this. So this is an interesting technique. If you add and subtract something in the denominator, then you can break it up. And you guys see how this is 1 because this is equal to itself in the numerator and the denominator. The numerator and denominator are equivalent, so it's equal 1 for all values of x. And then you can even graph this a little bit. I don't want to scare you guys because that's not really an obvious thing, but I'm going to do it just so you can see it. I don't anticipate you having to worry about this right now. But this is a skill thinking about end behavior of a graph, right? I mentioned with polynomials, we can think about end behavior. If they go off to infinity and negative infinity, what exactly is going on here? Well, in this case, you can also think about end behavior. You can think about end behavior in that if x is very large, or if x is very small, this term is about 0. Does everybody see that? If this is a large number, then I'm subtracting 1 over a large number, and 1 over a large number is about 0, meaning that our function is approximately equal to 1 if x is large. So I'm not even going to graph the whole function, but I just want to point that out to you, the importance of understanding end behavior. I don't know if it comes from the top or the bottom. In fact, I would expect it to come from the bottom if this is a positive number, but I'm not sure. But I'm going to tell you what's going on here right now is it's going to approach 1 as x goes to positive infinity and negative infinity, because this term kind of goes to 0. Does that kind of make sense? This is kind of an interesting side example. Again, not something like I think you directly have to worry about, but I think if you understand it, it will help with everything. Help reinforce that concept of end behavior and help introduce more ways of looking at breaking up rational functions other than the traditional definition of division. Anyway, I will do one polynomial long division example in here. Looks like here is one here. Let me just look at it real fast. Okay, yeah. So this one wants us to divide x cubed plus 2x squared minus 5x minus 6 divided by x plus 1. Okay, so I'm going to set this up. I'm going to do x plus 1. This is a little bit close here, but that's okay. And I have the x cubed plus 2x squared minus 5x minus 6. So when you think about these, this is a linear term, so it's going to go into this by x squared, right? This goes in there. Sorry, I am messing up my notation. It's x cubed plus 2x squared minus 5x minus 6. So the x plus 1 is going to go into the x cubed x squared times, right? And it's going to go into this term. We won't worry about that yet. So anyway, if I multiply the x plus 1 times the x squared, what do I get? I get the x cubed, and then I get this plus 2x squared. And then I subtract, and then this is just 1, because this is a 1. I'm copying things down wrong. So then I get 1x squared here. So now the question is, how does x squared go back into this, right? After I bring down this minus 5x. So this x goes into x squared once, so it's plus x. right? And then I do the multiplication again over again. So then I get x squared plus x, and then I subtract. I get minus 5x minus x, I get minus 6x. Now I can bring down the minus 6, and then I do the same thing over again. I say that this is a minus 6 because x goes into minus 6x minus 6 times, right? X times minus 6 is equal to minus 6x. And I do the multiplication again, minus 6x, and then minus 6. Then you'll notice this is 0. So if I divide this, it goes, this function, the x plus 1, goes into this function evenly this many times, meaning that x plus 1 times x squared plus x minus 6 is equal to x cubed plus 2x squared minus 5x minus 6. All right, does everybody kind of see the algorithm there?
Yeah.
Yeah, okay. That's, you can break up any fraction pretty much using that, any rational function. And then you can see how this relation sort of comes in, because I'm saying I'm dividing this by this and I'm getting this number. So if the answer is, if I have x cubed plus 2x squared minus 5x minus 6 divided by x plus 1, I get the x squared plus x minus 6. But if you multiply this to the other side, you get it like that. So the important thing here is, if you're given a complicated rational function like this, if you're given some like f of x is equal to this, that looks really hard to graph. That looks a lot more complicated. However, if I use the polynomial long division, I find out that it's actually really just a parabola. And then this is completely equivalent to this, right? So this is just a parabola. And then the parabola, I can graph that because we already know how to graph parabolas. I graph the vertex, I can graph everything else, I can plot points. And it's essentially exactly the same. The only difference between this and this parabola is the fact that if I plug in -1 to our original function, you kind of have problems here. You get a 0 divided by 0 error at -1, but it's not an asymptote because it goes in evenly. If I can factor out, then it's not an asymptote. But still, if I plugged in the -1 here, there's still issues, despite the fact that this simplifies to this. So then how all that equates in terms of is the graph. It's just going to be what the normal parabola is. In this case, this parabola, I think I can factor that. What if it was x plus 3 and x minus 2, right? So this is going to have a 0 at minus 3. It's going to have a 0 at positive 2. And it's going to be upward facing because the end behavior is positive in both directions because it's a parabola with a positive coefficient. So the graph's going to look like this. However, at x equals -1, there's actually going to be a little bit of a hole there. I don't know if he's talked about that, but at -1, this function doesn't exist. But everywhere else, it abides by this parabola. And you can see it wouldn't exist at -1 because then there's still the division by 0 error, even if we factor it out. Is what I'm saying making sense? How we can connect polynomial long division in terms of graphing functions.
Yeah, it makes sense.
Okay, thank you. All right, well, like I said, I didn't prepare anything today because I didn't get any information to him about what to cover. So I'm open to suggestions if you guys have questions. If not, we can end early if you want to, but I don't really see much else going on in section 4.3 though. It looks like it's mostly just the division. There's this one interesting theorem in 4.3 I'll mention. I have a new piece of paper for this. This one's called the so-called factor theorem. So if we take f of x as a function, more specifically a polynomial, if f of c is equal to 0, then x minus c is a factor. So all polynomials can be written as a product of their factors, right? All polynomials, even if they don't have real factors, right? So like even like x squared plus 1, like I said, this is an example of a graph that exists above the x-axis, right? Well, you have talked about imaginary numbers in this class. F of x is equal to 1. So you should be able to recall that if I plug in x equals plus or minus I, then this function goes to 0 because I has the property that I squared is equal to -1. So f of positive I is equal to I squared plus 1, which is equal to -1 plus 1, which equals 0. And f of negative I is equal to -I squared plus 1. And then the negative goes away, but the I squared still is -1, so this is still -1 plus 1, which goes to 0. So I can write this function, f of x, is equal to x minus I times x plus I. All polynomials can be written as a product of their zeros, or I guess their roots. Again, this is kind of harder to conceptualize this example because it doesn't actually cross the real x-axis at any point. But if you should see, at least with the algebra, if I multiply this out, I get x squared plus ix from the outside terms, minus ix from the inside terms, and then minus I squared on the end, which is just these terms cancel. I get x squared minus I squared. Well, I squared is -1, so minus I squared is just plus 1. So I can rewrite this function as a product of its factors. Now, if something does cross the real axis, then that's a root. So a function can be always written as a product of its roots. So if f of c is a 0, then f of x can be written as x minus c as one of the terms, and then times something else. Because plugging x equals c in here can clearly show that plugging x equals c would result in the function equaling 0 at c. So that's kind of the point of understanding here, is kind of understanding polynomials at a little bit of a deeper level as a product of roots. And if something is a 0, or if something is generally a root without even having any real zeros, then that would be one of the terms in that product if I write the polynomial in this sort of factored way. Okay, so it's kind of a deeper idea there behind that theorem, but that's one point I wouldn't mind trying to get across. Hopefully that makes sense to everybody. Okay, well, like I said, he didn't give me anything to cover, so I'm happy to go over more if you guys want to, but otherwise we can stop here, or I can stick around and answer questions if you want to about and officially. Okay, is that fine with everybody?
Yeah, thank you.
No problem.
Thank you.